So we got an introduction to climate change. So just to recap, we said climate variability is when something like temperature or precipitation goes up and down from year to year, decade to decade, maybe century to century. And we said climate change is somewhat of a generic term, but it generally means things are changing in one direction for a decade, 2 decades, and so on, and there is no fixed time scale. But climate change has happened in Earth's history over many time scales. In this lecture, we will look at what is called tectonic timescale, which is many millions of years where geological changes happen, like continents moving and reconfiguring, mountains building, etc. If you are a teacher and trying to build a climate change course, you will see that this module can stand on its own, which means you can actually drop it from the main course. But you will see there are many interesting, significant, large scale changes that happen on these time scales. Some of them will have a implication for future of our climate under global warming and anthropogenic effects and so on. So you can listen to this, pick the good points, and then see how you will build it into your course, whether you will completely drop it or not. For that, let's look quickly at the geologic timescales. So when we do the geologic timescales for the whole period, the eons are very easy to remember. They are split into Hadean, Archean, Proterozoic, and Phanerozoic. Hadean basically comes from Hades, which means hell. That was the time when the continents were still forming, solar system was still undergoing lots of changes, lots of meteorites were crashing into Earth. It's the so-called primordial soup time when a lot of volcanic activities and so on. Archean is from the word archis, which means the beginning. That's where we know that the first evidence of life is available. About 3.85 billion years ago was when there is chemical evidence that there were biotic materials being produced and being solidified into rocks, and there is evidence for that. Proterozoic basically means early life. That's where we begin to have more clear evidence of more sophisticated life, more complicated life. And Phanerozoic is visible life, where we begin to have lots of fossil evidences and so on. So we don't need to know all the details, but it's good to remember these broad scales, and you can obviously zoom into, for example, the Phanerozoic and look at the Paleozoic, Mesozoic, Cenozoic, and so on. So the tectonic timescales have happened over these long time scales, and they have affected the evolution of life, evolution of vegetation. For example, the dinosaurs obviously went extinct, and probably you all heard the story already. It's related to the crash of a meteorite, which would cause large climate changes. So we need to look at what are the kind of changes that happen if a meteorite crashes into Earth. So let's kind of look at a sort of an animation of how continents have moved over the last 600 million years. So this is the configuration that was there. There was continent at the southern pole. Things started to move northward by 280 million years. You can see that the continents are quite distinctly different from where we started from here. So how do we know these things? How are these things reconstructed? How do we know that a certain continent was at a different latitude compared to the present, or 600 million years ago compared to 280 million years ago? We'll see how those are done. So by the time the dinosaurs went extinct with the meteorite crash and so on, you can see that most of the modern continental configuration was coming into place. So you can already see the South American continent, North American continent, Africa. The rift looks very different than at present, and you have this direct pathway here. So the Indian Ocean and the Mediterranean and so on are not separated yet, and more importantly, India is still to the south of the equator, which means you didn't have the Himalayas, you didn't have the monsoons, for example, and Australia is still to the south of the equator, which means the Indian and Pacific Oceans were completely connected. There was no barrier. Now there is Indonesian seas and the New Guinea and so on. So here is the present configuration. Here is India, here is Himalayas. You can see this connection has been changed quite dramatically. The water has to go this way now, cannot just flow across, and the rifting of the African continent is quite different. The Mediterranean Sea is quite distinct here. The Atlantic, Pacific and Indian Oceans are fully configured, and Australia is now quite far north, and Antarctica is glaciated again. So, Antarctica is not always glaciated. So, if you go back 65 million years ago, you can see that there is no glaciers on Antarctica. So, these are kind of the tectonic changes we are talking about. Plus, when Himalayas came into existence, we began to have the monsoonal circulation during the summer and winter completely changing and producing rainfall seasons and so on. So, in addition to the paleo proxies we looked at and the way we date things using various isotopes for different time scales, the location of the continents can be inferred from using the magnetic information. So, you find rocks on those continents, date the rocks and see how old they are, and see what are the magnetic signatures on those rocks. So, essentially, if a rock is further to the north, the magnetic lines will be less angled than if they are at a lower latitude. So, if it is smaller angle than at higher latitudes. So, you use this information of magnetic lines and their angles to figure out in the past where they would have been. If you track Madagascar, for example, it keeps moving southward and then merges with other continents. You use isotope dating techniques and magnetic information buried in the rocks on those continents to figure out where they were in the past. So, we will keep coming back to these, but just to give you a quick example, if the continents were very differently arranged, you would expect that the regions where the continental shelves exist, the regions where the various pathways between different oceans exist, the way the ocean currents are and the winds are, because the equator to pole temperature gradient would have changed, climate would have changed, in addition to where the mountains are and so on and so forth. So, the continental shelves are typically very important for biological processes where water is very shallow and upwelling and nutrient supply and other things affect evolution or the colonization of life that was in the ocean onto land can happen starting in shallower seas, and when the sea level changes they have to adapt to live on land. So, many such changes have happened. So, the climate changes, life changes. If life changes, then oxygen and carbon dioxide will change. So, atmospheric composition will change, which means ocean atmosphere interactions will change, and again climate will change in return. So, there is a whole feedback loop, and we will look at some particular examples of this. So, here is a quick time scale of that. If you go back to the origin of the solar system and the birth of Earth 4.6 billion years ago, there have been times when extensive ice sheets existed on the planet, and you can see this is, remember, Hadean, Archean, Proterozoic, Phanerozoic and so on, and you can see the reconfiguration of continents as we go along. And there are multiple evidences that there were times when the globe was almost completely covered in ice or snow. Those are called Snowball Earth episodes. We do not understand exactly how they occurred. There is some theories which can become confirmed, but there are many ways in which the evidence for ice ages can be obtained from the past, that we will see some of them. So, as the continents move, where the continent is determines not just the climate, but also the weathering rates. For example, if the continent is in the deep tropics, warm temperatures, more rain means the rocks will weather faster, the weathering rate will be higher. And remember that weathering is basically taking carbon dioxide out of the atmosphere. So, that will cool the atmosphere. So, we will look at these kind of feedbacks. For whatever reason, the continent is in one place, creates warm temperatures and rain, but that increases weathering rate, that takes down carbon dioxide and cools the climate. So, that is kind of a negative feedback. And if the continent is near the pole, then it is easier to build glacier on land when it's in a cold, high latitude location. So these are the kind of things we worry about tectonic timescale climate change. So the other thing that we will briefly mention again that we mentioned before is that the solar luminosity itself has changed over time. So if you go back to 4.6 billion years ago, the sun was only about 70% as luminous, which means the energy coming in was 30% lower compared to the present. So over time, slowly sun has gotten more powerful. So at the present day, we are here. Okay. So what does that mean? Basically, there are physics involved in this, chemistry involved in this, nuclear fusion involved in this. Mainly hydrogen is the fuel. In nuclear fusion, it combines to form helium, and helium is heavier, so it increases gravity, but the nuclear fusion increases temperature and expands the sun. So the balance between the gravitational pull of the helium and the expansion due to fusion of hydrogen essentially ends up expanding the sun. So in about 5 billion years into the future, for example, sun will become so large that the earth will be completely consumed. But just in about 100 million years, the temperatures will reach boiling temperature of water. So will we still be in the habitable zone around the sun or not? Obviously, that is too far away. We don't have to worry about it. But the fact is that solar luminosity increases year by year, and that also should add to climate change on million-year timescales. So there are other issues associated with it, in the sense that if sun was 30% less luminous and there was less energy, and we have evidence that there was liquid water, then how would you have maintained temperatures warm enough to keep water from freezing? So that the theories basically go on to look for what were the mechanisms with which greenhouse warming was happening. Remember that this was before plants existed, before photosynthesis started, which started, as we will see a little bit later on, is much earlier, about 500 million years ago, 300 to 500 million years ago. So methane, there were a lot of creatures, there were bacteria and archaea that were forming methane, and methane is 25 times more powerful as a greenhouse gas. So you would have probably had more methane, so the greenhouse effect of methane was high enough to take the lesser energy coming from the sun and still create temperatures warm enough to keep water in liquid form. Okay? So carbon essentially has played a role. Methane is just another form of carbon. Methane is highly oxidizable, so it doesn't stay very long in the atmosphere. As long as it's exposed to oxygen, it gets converted into carbon monoxide and water and then carbon dioxide. So carbon dioxide essentially has played a role in climate change at all time scales. So even though we say tectonic timescale climate change, tectonic processes essentially affect carbon dioxide, greenhouse effect, and that's how they affect climate. So here it is, just looking briefly at carbon cycle, which we will get into more details a little bit later on when we come to climate change in the modern context. You just look at kind of the reservoirs, how much carbon is stored in various things on the planet. On average, vegetation has about 600, the units here are what are called gigatons. Giga is basically 10 to the 9. You can convert it to grams, it becomes petagrams, which is 10 to the 15 grams, and so on. So 1560 gigatons, 610, and what you will notice is that atmosphere is a relatively small reservoir of carbon because it's light and it cannot hold on to many forms of carbon, just carbon monoxide, carbon dioxide, and methane. Ocean, on the other hand, is a huge reservoir. Just the top of the ocean near the surface where photosynthesis is happening because there are enough nutrients and light, there is 1,000 gigatons. But the deep ocean has 38,000 gigatons. So you can see the huge difference. This is why the ocean is so important. It's a deep, huge reservoir of carbon. Okay? And the sediments and rocks have 66 million gigatons of carbon. Okay. So, there are exchanges between them. As you can see, there are fluxes in and out of the ocean. Photosynthesis takes up some amount, respiration and outgassing puts some of it back. There is carbon flowing from land onto the ocean, soils are taking up some, photosynthesis by vegetation is taking up some, and so on and so forth, and there is exchanges between the deep ocean and the surface ocean, and the stuff that falls to the ground gets buried in the sediment over time because of pressure and temperature, gets converted into sedimentary rocks and metamorphic rocks, and so on and so forth. So, carbon is getting constantly cycled, but here we are only talking about CO2 and inorganic forms of carbon. There is also a organic carbon cycle, which is photosynthesis in the ocean and on land, and burning of the natural forest fires or burning for agriculture and other things, and there is humus or organic carbon in the soil that insects are digesting, like termites, converting back into inorganic carbon, or some anaerobic respiration that converts it into methane. Carbon gets buried deep into the ocean, and so on and so forth. So, there is a organic carbon cycle and there is an inorganic carbon cycle. They kind of work together on long time scales. Obviously, everything has to balance, in the sense the volcanoes are putting carbon dioxide into the atmosphere and weathering is taking it down. So, on a very long time scale, the weathering rates have to basically balance the volcanic input of carbon dioxide into the atmosphere. The chemical weathering, as I mentioned, removes atmospheric CO2. This is the geologic time scale process on thousands, hundreds of thousands, millions of years. There are silicate rocks and there are limestones, and essentially water which dissolves carbon dioxide very easily, or CO2 is highly soluble in water. This is why you make things like Thumbs Up and Coca-Cola and Pepsi, for example. You put carbon dioxide into water, that forms carbonic acid and it dissolves rocks and produces calcium carbonate, which flows into the ocean. There are additional reactions. Calcium carbonate is getting split into calcium and bicarbonate and carbonate and so on, which we won't get into the details at this point. But the one thing you have to remember is that weathering is a constant process because there is rain somewhere on Earth all the time. And as I said, as continents move and climate changes, where the continents are, what temperature and precipitation they are exposed to determines how much weathering happens. So, the weathering rates will decide how the cooling and the warming happens. The climate controls on weathering also comes through biology. Okay, so biology is responding to temperature and precipitation. So, this is again the average from equator to pole on both sides, averaged over all longitudes, as we call it the meridional section. So, the temperature is warm in the tropics and cold at the high latitudes, and there is an asymmetry. Southern pole is much colder than the northern pole. Precipitation is also asymmetric. The so called intertropical convergence zone, for which there is a separate module, is located to the north because there is more land to the north. Remember, land has lower heat capacity than ocean. So, land heats up faster. If you have more land, there is warmer temperatures and the rain band moves to where the warm temperatures are. So, it is to the north of the equator. And there is at higher latitudes also some rain. If you remember from the Hadley cell, there was rain in the tropics and at mid latitudes, and poles were dry, subtropics were dry, right. So, the production of photosynthesis increases basically in these bands. So, here it is going from minus 10 degrees centigrade, there is hardly any production. As you warm, the primary production or vegetation produced goes up, rainforests, tundras, boreal forests, and so on and so forth, right. So, what happens? We already mentioned a little bit yesterday that every time you have vegetation, they set roots, they take up water, they capture carbon dioxide, they produce organic matter, and they run it off into the ocean. And on rocks also, moss and lichen and other things grow and they set roots and they loosen the top surface of the rock and increase weathering rates. So there is something called weathering rates, chemical weathering, that is directly controlled by climate through vegetation. So those also affect the processes. So there are essentially negative feedbacks from weathering. As I said, it's like a thermostat on various time scales. So if you made a change in temperature, but let's say by moving a continent from the higher latitudes to the tropical region, it will experience warmer climate. So it will increase temperature and precipitation and vegetation. So vegetation is higher at warmer temperatures on average. That will increase the chemical weathering. So that will increase the amount of CO2 being taken out of the atmosphere, which means it will reduce the initial warming. So this is a net negative feedback. Something wants to increase the temperature, but the processes then want to decrease the temperature. So it's just like a thermostat. You set the thermostat. If the temperature gets too warm, the AC will kick in and it will cool it. If it gets too cold, AC will go off and it will get warm again. Okay. The other way it can work is there is some change, you made it, let's say, colder, then the temperature will decrease, vegetation will decrease and precipitation will decrease. That will reduce the weathering rates, which means you are reducing the amount of CO2 being taken down, which means it will reduce the colder climate. So you have this negative feedback from weathering. So if you want to go back to anthropogenic climate change and global warming, all the carbon dioxide we are putting in now, let's say we disappeared or we suddenly became so good at reducing carbon that we stopped putting any more carbon into the atmosphere. In the next hundreds to thousands of years, weathering rates will slowly take down all the carbon dioxide we have put into the atmosphere, and it will put it into the ocean and bury it in various places. That's the weathering thermostat. Okay. This is just to reaffirm that these kind of processes have worked on tectonic timescales. So whether it is reduced solar luminosity in the past or warming because of continental movements, the solar radiation and other processes were definitely balanced by stronger greenhouse effects in the past, whether it's because of methane or higher amounts of carbon dioxide. We'll see some examples. And in the present, with stronger radiation compared to the past, the greenhouse effect has reduced. So essentially we are locking up more CO2 in the rocks during this weathering process. Okay. So the Earth's structure is needed to understand a little bit of why plate tectonics happen. We won't get into the details of geology, but I think you're all exposed to the basic structure where you have the core, the mantle and the crust. The core has the inner core and the outer core, and the mantle has a plastic asthenosphere which is about 350 kilometers deep, and a more rigid lithosphere where the plates move. So this is where the high temperatures are mashing together and creating magma which can burst through and come through the volcanoes. And you have the crust where you have the continental crust and the ocean crust. Continental crust is almost 30 kilometers thick, whereas the ocean crust is much less, order 10 kilometers thick. Ocean is very heavy, so continental crust is more compacted. Both are igneous rocks. This is more a basalt and this is granite. So this is lighter and this is darker. So in the past there have been glaciations. So this is now going back to 500 million years, which is where which is the period we called Phanerozoic, visible life. We will see a little bit later on that this is where an explosion of many new species happened during the Cambrian. So this whole period is called post-Cambrian. I'm throwing a lot of terms, but I'm sure you can look it up in other modules that are provided. So North Africa had quite extensive glaciation during the first few 100 million years after the life exploded. The quickest explanation is that photosynthesis and large scale plant life evolved during this period. They quickly took down a lot of the CO2 because photosynthesis accelerated and there was lots of vegetation, and suddenly there was reduced greenhouse effect and glaciation happened all the way into lower latitudes like North Africa. And there is evidences, you can find various geochemical evidences to say, like glacial striations, stellites, moraines, and other things like banded iron formations. There is a separate module for that, which show that there was extensive glaciation. Closer to the recent past, 300 million years ago to 50 million years ago, various places like South America, Australia, South Africa, Antarctica, India had various levels of glaciation, less extensive or more extensive. What do we mean by glaciation over India? Essentially, India was further south during this time, right? It was still way to the south of the equator. So, it was at a latitude where you could still build land ice on the Indian subcontinent. More recently, obviously, in the last 65 million years, we will come back to more details of this period. Antarctica has huge glaciers and North America has glaciers, Eurasia has glaciers. Obviously, Himalaya also has glaciers. So, how are these glaciations, which are obviously climate change, related to tectonic processes? That's kind of the question. Here is the distribution of current tectonic plates. The Pacific plate is big and it's the youngest one, the Atlantic plate and the Somali plate, Asian plate, Indian plate, and so on and so forth. So, the details matter, the processes, because the plate margins are divided into divergent margins or convergent margins. So, the plate margins can be going rifting apart and going away, in which case the magma can come up through that rift, or they could be converging, which means one plate is ducking under the other plate, and you can have this kind of complex configurations. Again, we use magnetic line information to see where the plates were and how they have moved over time in different latitudes. More recently, over the last 100 million years, the magnetic reversal information that is locked in various parts of the oceanic crust have also been used to understand how quickly the ocean crust is constantly forming and how often the magnetic polarity is switching on Earth and so on. So, I will not go into the details of this, just because these are just the processes you need to be aware of that are important for deciphering past changes. So, if you look at the current configuration, Africa and South America almost look like they can be put together like a jigsaw puzzle if you move it. On the other side, you have Arabia, India, Madagascar, Antarctica, and Australia. Alfred Wegener proposed this in around 1914, 1915, and people thought he was crazy, because he just looked at the morphology of the continents and said, look, if I just put them together, it's like a jigsaw puzzle. And at that, till then, people didn't know that continents can actually move. And in fact, only after he died in the 1960s that all the evidence came together to show that actually continents do move. But as soon as it became clear that they move, the geochemistry, magnetic information, and other evidences have been put together to build all these tectonic timescale climate change narratives. So, it's amazing how the guy just saw the configurations and said continents must be moving. Okay? So, here are the glacial striations created by a glacier formation on land. So, the movement has obviously happened along these lines. The South Pole position 500 million years ago, 430 million years ago, 380, and so on and so forth. So, the magnetic pole has moved, which means the continents have moved over the magnetic pole. So, Africa was glaciated when it was over the South Pole position, and now Antarctica is over the South Pole position. Australia has moved north, South America has moved north, and so on and so forth. You can also use then the models. Once you have the location of the continents, we can go back and take these numerical models. See, the beauty of the numerical models is they are they're solving mathematical equations given where the oceans are, where the lands are, where the mountains are, and so on and so forth. So you can just go into the model and move the land around, and you can say that we know the past configuration of land during the so-called Pangea was this way. So then you give solar energy of that time and you see what circulation evolves. So this is showing precipitation in millimeters per day. So where it is green, it's more than 3-4 millimeters per day, which is like a monsoon. It's pretty heavy rain. 2 to 4 millimeters of rain here, and these are basically like Rajasthan, they are deserts. So what is amazing about this? Here is the equator, the land configuration is this way, and the climate is remarkably different than present. So the subtropical regions are still dry like today, but the deep tropics are also very, very dry. But the ocean is getting a lot of the rain. Okay. So here is the soil moisture. Obviously, soil moisture is basically the moisture content, that is water that is in the soil, that is very critical for vegetation, for agriculture, and for energy exchange with the atmosphere. In the dry desert, the atmosphere can get very hot because the radiation can heat the land very fast during the day, and during the night it can also cool very fast because there are no clouds. Okay? And that would be a good exercise for your students. Why do deserts warm very fast and cool very fast during a day? So you can see that soil is very dry in the regions where there is no rain, and in the regions where there is rain, obviously soil moisture is fairly high. It's measured in terms of water level in centimeters. So the temperature obviously are also, this is the winter hemisphere here and this is the summer hemisphere. You can see that the winter hemisphere has cold temperatures less than 0 degrees centigrade. Much of the summer hemisphere is very, very warm. Okay. How do we know these things? How do we know whether these models are right or wrong? Basically, you have to go find evidences for rainfall changes. So there are, we didn't mention this as a paleo proxy yesterday, but there are what are called evaporite deposition. So if you take cores in the lakes or the oceans or other places in land where you can find old sediments, when there is more rain, the amount of salt or other evaporites, the minerals that are released when evaporation of water happens, are very less. So there is some gap here, we don't have good data, but you can see that when evaporites increase in Pangea, it corresponds to these drying relative to today. So in fact, these are kind of the rock salt deposits that are measured in one of these locations. And the good story that confirms this kind of evaporite relation to precipitation is in the Mediterranean. If you remember, Mediterranean Ocean has a very small opening through the Straits of Gibraltar to the Atlantic. So the Atlantic water is light, it comes in, there is a lot of evaporation in the Mediterranean, and that heavier water gets out into the Atlantic. So somehow this exchange was closed off about 6 million years ago in a period called the Messinian. If you closed it off and the Mediterranean keeps evaporating, it will keep depositing salts. So there are mountains of salts at the bottom of the Mediterranean about 6 million years ago. It's called the Messinian Crisis, which means now you have to go back and figure out what would have closed the exchange of Atlantic and Mediterranean water through the Straits of Gibraltar. So these are kind of the evidences. So it's almost like finding a dead body and you have to prove how it died. You have to find all the evidences to put together the story. This is just the changes in circulation. So these are the seasonal pressure and winds, and the interesting thing here is that there was something called a super monsoon during the Pangea in the summer hemisphere. So these are very heavy rains, okay, greater than 4 millimeters per day. So if you take the monsoon season and take average rainfall of 4 millimeters per day, you can see how much rain you will get in one season. Compare it to the average rain we know is about 900 millimeters during the monsoon season over India. how much does that amount to? So why is this called a super monsoon? Okay, very heavy rains. So this is a very clear example of how you find magnetic geochemical evidences for the continental arrangement during the past climate. Then you use models to say what kind of climate would have existed during that time to explain the chemical evidences. Okay. The other thing we need to know is how does tectonic motions and processes control carbon dioxide in the atmosphere. As we said, the tectonic processes can directly affect climate by building mountains and creating monsoons, or making the oceans larger or smaller and so on, or moving north and south and creating glaciers, but they can also control the amount of carbon dioxide. So essentially you have ocean crust where you have hot spots and so on, like Galapagos and Hawaii, where magma can come out and alter the atmospheric carbon dioxide, or there are boundaries where the continent's ocean crust subducts, like when the Atlantic ocean crust is forming and spreading out, it will duck under the American plate and the African plate. At those plates also you will have magma forming and creating volcanic activities. So volcanic activities on long time scale, tectonic time scale, is the process that is controlling the atmospheric carbon dioxide levels, which means also ocean carbon dioxide levels, and it's the weathering on those tectonic time scales that controls the balance, the thermostat. So those are very, very long time scale processes. You have to assume a lot of things, or you have to hypothesize how changes have happened and then try to find evidence to support your hypothesis. So sometimes you find evidence like these evaporites, for example, and you know that there must have been changes in precipitation amounts. Then you have to go and figure out how that could have happened. In this case, you could use the model and confirm that the evaporite deposition is explained by changes in precipitation patterns. So sometimes you have to assume that the spreading rates at the ocean crust, where the new ocean crust is being formed along the so-called ridges, have not been the same. They change over time. These are harder to confirm because you have to find evidences for spreading rates, and you can basically, when the spreading rates change, the volume of the ocean changes. If it spreads very fast, then the plate's crust subducts under the plate and the volume can be reduced. If it spreads slowly, then the volume can be increased. We won't go into the details, but just remember that the spreading rates affect the configuration of the oceans and the continents. So there is a hypothesis that such a thing happened, and then you build potential feedbacks and then look for processes whether that can confirm or deny this feedback that you are hypothesizing based on the spreading rate. So we are getting close to 45 minutes. I think I will stop here and come back to the Blagg hypothesis, which relies on arguing that spreading rates have not remained constant over time of Earth's evolution. Why is it called Blagg? It's basically the authors who wrote this paper arguing that the C4 spreading rates have not remained the same. So to kind of summarize quickly what we looked at the evolution of Earth briefly, the movement of the continents. They were all kind of bunched together at the southern pole. They've all been kind of moving north, and we know that they are continuing to move north. So in few 100 million years, they will all go all the way to the North Pole, and then they will begin to move back. So right now, India is, for example, still moving north. So Himalayas are still rising at 1 or 2 centimeters per year. Australia is still moving north at about 3 centimeters per year. So all the continents are still moving. African rift is still increasing. This is why you continue to have earthquakes here and there and so on. So the tectonic movement is a continuous process. So the climate change processes associated with tectonics, do they have any relevance for global warming? That's the big question. But just understand the processes of how climate changes happen, how tectonics affects carbon dioxide, and then decide whether this chapter should be included in your climate change course or can be kept separate. See you next time.